I'd like to introduce Richard Feldman. Richard is one of our favorite speakers who had made the great choice or the mistake of actually moving to Philadelphia. So now he gets to speak at ATE every year. And we follow, Richard is a big ML enthusiast, a big functional programming enthusiast who has first made a big name for himself in Elm, and then I guess he didn't think that Elm was enough on the front end. He wanted to make it on the back end too, so he developed his own language called Rock, and he's going to be talking about developing desktop applications with Rock today.
All right, thanks, Mark. Let's dive into it. Share my screen. This is native desktop apps in Rock. I'm Richard Feldman. Can everybody see okay? Great. All right. So back in 1998, a lot of things were different. This is a music player, a physical music player back in 1998. You can tell it was 1998 because if you look closely, you can see that there is both a CD player in the top as well as a cassette player. Another thing that was out in 1998 were desktop apps like this. This was Microsoft Outlook from 1998 or thereabouts. And another one was Winamp. I spent a lot of time listening to music through Winamp around this period of time. This actually is not a screenshot of original Winamp from back then. This is actually a screenshot from a web app called webamp.org. Pretty cool. Somebody made a faithful recreation of Winamp in the browser, so you can try it out even if you're not running a Windows machine. And I actually listened to a whole playlist on webamp.org while making this talk. One of the things that was big back then was this idea of a native look and feel. So one of the criticisms of Winamp was that it did not have a, quote, native look and feel, which is to say it didn't really look like a normal Windows desktop app. Normal Windows desktop app being something more like Outlook. For me, I don't know, I kind of like that aspect of it. I liked how Winamp looked. I thought it had its own style and it was a pretty cool style. I was reminded of how games really never had a native look and feel to them. Like this is a game from 1998. You can see it has its own style that's quite different from Outlook. And actually, Winamp honestly kind of looks more like a game. So I have several fond memories of Winamp from 1998. One is that it had this sort of distinctive and, in my opinion, nice style. It had light resource usage. When I was running Winamp, even on my 133 megahertz Pentium computer back then, I was running it in the background alongside, sometimes multiple other apps, and I didn't really notice it. Also, it ran really fast. There weren't really any like loading spinners or pauses or like lag or anything, at least not that I can remember. So these were all sort of fond memories that I had of Winamp back in the day. Now, many modern desktop apps are sort of different in terms of user experience from what I remember of Winamp in 98. So, okay, the non-native look and feel part, that's definitely still alive and well, but they tend to be a lot more heavyweight in terms of resource usage. Like sometimes my computer is running slowly and the solution is just to like quit some of these desktop apps that don't feel like they're doing that much and would need to be using that much of my system resources. Also, delays happen all the time. I mean, not just in music players, but all sorts of apps that I use, I find myself sitting and just staring at the screen, waiting for something to happen. That's weird because, I mean, computers are like an order of magnitude faster than they were back then, like 133 megahertz versus, 1 gigahertz would be slow today. And yet, delays all the time, heavy resource usage. I saw this tweet and it really resonated with me. Are M1 Macs yielding a brief and golden window of highly responsive UIs where frameworks and libraries haven't yet had enough time to compensate with additional overhead? I suspect he's talking not just about desktop apps, but also about like web apps and maybe even mobile apps as well. But it's kind of a reasonable question. I mean, we've had sort of a slow and steady increase in CPU and other hardware performance improvements. The M1 Macs were sort of like a pretty big step up, and you got to wonder if there weren't such a big step up, would it be noticeable how much of a difference they made? So I think web apps are a big part of this story. So back in 1998, you didn't really have web apps like webamp.org. I mean, this running in the browser on JavaScript would have been totally unthinkable back then, in large part because JavaScript was way too slow to do something like this, but also because of playing music and things like that. But also, I mean, web apps by and large were not a thing because web pages were a thing. You would have HTML and maybe JavaScript, maybe CSS, but honestly, maybe not in a lot of cases. Web apps, of course, have sort of taken over the world. I mean, they're the most common apps that we use day to day tend to be web apps these days. And pretty much all of them have this non-native look and feel thing to them. So that part's similar. But other than that, I mean, first of all, when it comes to delays, you've got unavoidable network latency. every time you visit a web page, the first thing it has to do is download the code to execute, versus like a native app, it just loads immediately because it's just right there on your system. There's nothing to download. Also, there's some question marks around like how fast the app can possibly be if it's written in JavaScript or compiles to JavaScript. So there's this sort of performance cap on how fast a web app can run compared to a native app, because it's got to be running JavaScript. There's no way to, have the browser execute like C or C++. That is until WebAssembly becomes more widely used. Like today, WebAssembly exists. You can definitely use it for things. But by and large, the overwhelming majority, 99.9% of the web apps that are being used today are written in JavaScript or compiled to JavaScript. And then on the server side, like, okay, yes, servers can be kind of slow, but of course, the solution to that is just throw more hardware at it because it's somebody else's machine, so maybe it's fine. So culturally, there are quite a few differences between how web apps are made and like how people think about performance and what people's expectations are around performance and resource usage compared to native desktop apps. But there's definitely been a strong influence, I think, since web apps have become so pervasive in how people build desktop apps. So one thing is, I actually think that web apps have been largely responsible for the idea of a non-native look and feel going away. Like back in 1998, Winamp was this sort of outlier. It was sort of weird that Winamp didn't have a native look and feel. Most of the other apps that I was running on that machine did look more like Outlook, but these days it's not really a thing anymore, because I think web apps have sort of gotten rid of that. They've normalized having a non-native look and feel, which means that you don't really need to match the look of each OS. That's not really something that people expect the way that they used to in 1998. Another is language choice. So Winamp, as I understand it from what I was able to find on the internet, it was written in C, some combination of C and C++ originally, and that was super common back in '98 to build your desktop apps in C or C++. Now you contrast that to like web app server-side programming today. You could use any language you like. I mean, whatever you want. There's this cornucopia of options. You can use Ruby or Python or JavaScript or C, C++ if you want to, Haskell. I mean, really, sky's the limit, any kind of language you want, which means that we've all sort of gotten used to having this variety of options and being able to program in our language of choice. Now, that's true on the back end. On the front end, it's kind of a different story. It's like, we got two options. You got your JavaScript, you got your TypeScript. Choose. There's a lot of variety out there. I mean, yeah, it's like pretty much a monoculture with a few notable exceptions. Like almost all web apps that you're going to use today are written in either JavaScript or TypeScript. But it is true that you don't have to. For example, where I work, Red Ink, we don't use JavaScript and TypeScript. We use Elm on the front end, and we use Haskell increasingly on the back end. And this is such an unusual combination of technologies that it's actually become one of the main reasons that people like to apply to work here. That and the fact that we make software for English teachers and people like to feel good about what they're building. If that interests you, by the way, we're hiring. Take a look at noredink.com/jobs. But the point is that this is the type of thing that is unusual in the web app world. Usually it's JavaScript, TypeScript on the front end, and then whatever language you want on the back end. So I've been working on this programming language, like Mark mentioned, called Rock, rocklang.org. It's directly inspired by and a direct descendant of the Elm programming language. So it's definitely a work in progress. Like this is not something that's ready for like production use yet, but all the things that I'm going to demo today are actually working today. And so you'll sort of get a feel for like where the language is. Rock compiles to machine code or to WebAssembly. So theoretically, you could use Rock to make like a music player in your browser or something like that. Definitely, as we will see from the binary sizes later on, this would be quite large for a JavaScript app. So I would highly recommend using something like Elm to build your web app, unless you really need the performance of something like you're doing a music player or whatnot. But for this talk, we're really just going to focus on the machine code use cases, like actually building a desktop app, not a web app. And this is one of the use cases that I had in mind when designing Rock, is being able to build desktop apps. So when I was thinking about like, what do I want the experience to be like of being able to build desktop apps in Rock, I sort of partly went back to this nostalgia of 1988 and then tried to think about what were the things that I liked about that and what are the things that I like about modern app development, and how can we sort of blend these together and sort of try to get the best of both worlds. So this sort of led to these series of goals that I had for Rock as a language that you can use to build native desktop apps. So number one, definitely want to try to keep this programmer experience thing going. Like, don't want you to have to write them in C and C++. Try to make things ergonomic and feel nice to develop. Light resource usage, like we had from 1998. We didn't have as much options in terms of languages back then that were like really viable choices for building desktop apps. But once you did, build something like Winamp, it really had light resource usage in terms of like, system resources, and running very fast. Yes, definitely want to do that as well. And ideally, we could go a step further and also have cross-compiling. If you're not familiar with cross-compiling, let me take a second and give you a demo. So I've got 3 demos that I'm going to do here. All of these are not like native desktop apps in the sense of like a Winamp. These are all games because we're pretty early days. Nobody's actually built like something fully fledged enough to like build a real like, modern UI in. But with games, you just need some basic primitives like, lines and rectangles and circles and whatnot. So like I said, early days, but you can already sort of see what's possible with Rock today. So first demo is going to be made by Jared. This is Rocktris. And this one actually runs in the terminal. So I have not left the command line here. This is a viable way that you can make things in Rock. You're probably familiar with this game, but let's see. So we got, Rocktris right here. I'm going to drop that real fast. Let's see what else. Drop one of those. Yep, there's that. And okay. Oh, come on. I'm not very good at this game. All right, there we go. Cool. And then, if I just stack these up, then we're going to lose pretty quickly. Okay. So, for copyright reasons, we'll call this Rocktris and not mention what it might be inspired by, but you get the basic idea. It's a command line app, and it's a way that you can play games in here. Let's look at another one though that actually opens a window. So this one is called Fireworks. This one's actually a little bit less interactive. It just spawns some fireworks. You can see back in the terminal, it's sort of logging some things. So one of the cool things I can do with this is I press the up arrow, which I'm hammering on right now. It's going to keep increasing the spawn rate so we can get more and more fireworks on the screen at once. So this was developed by Brendan Hunsknecht, and he basically has been working on a Rock sort of like game engine like platform for making games, or at least like a proof of concept for that, using ECS, which is short for Entity Component System, which is a common thing that people do in games. So you can see the title here is Rock Simple ECS. Like, yes, it's just a demo of shooting some fireworks for now, but the point is more like how it's architected under the hood so that if somebody wanted to build a game on top of this, they could do it using an ECS system. Okay, now I mentioned cross-compiling earlier. So both of these examples have been me building an executable on macOS and running it. So if I do rock build fireworks.rock, it's going to just spit out a binary called fireworks, and I can just run it, /fireworks, and there it is. Now, so there's no like .js file that's outputting, there's no .wasm file. It just made a binary. So anybody else who's running Mac, I can just take that compiled executable and just send it to them somehow, and then they can run that program on their computer. Now, cross-compiling is where I do that same thing, but instead of producing a Mac binary, I produce a Linux binary from my Mac. So I'm going to do the same thing that I did before, except I'm just going to add --target Linux 64. And now, this is going to be a really impressive part of the demo. Ready? I'm going to run it, and it's not going to work, because this is a Mac. I can't run a Linux executable on a Mac. But I can run a Linux executable on Linux or on this handy dandy Linux VM that I've had spun up just for these purposes. So I've got this Linux VM. This is running a stock Ubuntu 20.04. I have a shared directory in here, which right now is going to be empty. So nothing in that directory. I also have that shared directory over here, nothing in there right now. What I'm going to do is I'm going to move that Fireworks Linux executable that I just built over to this shared directory. And now when I go over to my VM, it's there. And now let's see what happens if I run that. Remember, this executable did not work on macOS, but I'm over here on a Linux VM. And now when I run it on Linux, fireworks, hooray. Now the cool part about this and why it's called cross-compiling is that it's not so much that I am building an executable, but it's that I built this Linux executable that works and runs a graphical UI application, doing the same exact thing that it did on the Mac version, except that I actually ran it on Linux. So executable built on the Mac, but is able to run on Linux. Cool. So one more demo. This is going to be something that sort of, to some extent, combines the previous 2 demos. So Fireworks shows like graphics running, and then the Rocktris was like a game. This is another game which as you're going to be able to see, is not quite as complete as the other ones. It does look kind of neat. So this is Breakout. It's better if I, don't lose. This has like very minimal game logic to it. Basically, the only thing that you can do is you can move the paddle left and right, and then you can hit the ball. But that's it. There's no collision detection, so the ball just sails off the screen. Obviously, this is just put together for the purposes of this demo. This is not like a real game that's like actually fun to play. But the reason that I did put together something that was at least that fully featured was so that we could sort of go through the code. So Brendan wrote the fireworks demo. Jared wrote the Rocktris demo, but I wrote the Breakout demo so I can sort of demo it. One other note about the Breakout demo is that it is actually using like hardware acceleration. So this is actually like going straight to the graphics card, which has pros and cons. Like one pro of it is that if we wanted to put like a ton more stuff on the screen, all this is being rendered via the graphics card. So it would be able to, be hardware accelerated. But a downside of that is that it tends to use more memory than the other approaches, as we'll see later when we talk about some like memory usage and hard disk statistics of these apps. Okay. So before I demo the code for Breakout, I actually want to show you sort of the skeleton of like what Breakout is built on top of. So this is a Hello World app built on the same platform as Breakout is built. So I'm just going to go sort of line by line here because there aren't that many lines. App Hello basically says like hello is the name of the executable that we're going to produce here. So when you build this program, it's going to spit out an executable named hello. Packages. So this is basically normally where you would specify like your dependencies. So like in Node.js, you have like a package.json. In Rock, this is actually specified like right here in the file, like the root of your application. So I've only got one package called breakout-pf. So this is basically pf is short for platform. So this is the platform that I use to build Breakout on. And so I'm using the exact same platform for this this Hello World example. Imports, this example is so simple it doesn't actually have any imports, and then provides program model to PF. Basically, these two pieces are sort of telling the platform about the parts of my application that are specific to my app, like my Hello World app. Everything else, like the platform is like, I don't need to know about whatever else your program is doing, but I do need to know what is your model and what is your program function for starting up the program. So model is defined right here, and then program is defined on the last line of code. Don't worry if you're not following all of this. This is not supposed to be a comprehensive tutorial. It's just sort of like, here's a sketch of like the basic parts. Okay, so my model is the term that I'm using for my application model. This comes from the Elm architecture. So if you're familiar with Elm architecture, a lot of these concepts are going to sound familiar to you. Because this is Hello World, I decided I'm just going to store one thing in my application state, which is text. I could have just not even stored that and just say there's nothing in here and just hard coded Hello World, but I figured I'd at least show like a little bit of application state. So init was where I would init my application state, like initialize it. So here I'm just saying, okay, I'm initializing this with the text Hello World. Update, this is basically only for interaction, like events would come in and I would potentially change my model based on the events. But since this is Hello World, not going to do any updates. And then render is basically every time the platform wants to re-render the screen, it calls this function. It says, here's your current model, so your current application state, return whatever you want to be rendered. In this case, I'm just returning some text, which is model.text. And then finally we have a program, which sort of hands all of these off to the thing. So let's demo that real quick. Rock hello.rock. And it's going to spawn a window. And hopefully it will just say hello world like we had in the text there. There we go. Cool. So this is Hello World. This is the basic, like, if you want to build a native desktop app in Rock that can be cross-compiled and all that good stuff. In theory, this is the bare minimum that you would need. It's like 14 lines of code. Shorter without line breaks, whatever. And basically all of the heavy lifting for all of this is coming from the platform. Like the platform is doing all of the setup work for all the window initialization, all that stuff. You can think of the platform as something like a framework, although if you take a look at some of my other talks on Rock, which you can find at rocklang.org, including one from Philly ETE last year, I talk about platforms, there's actually more going on to them than a framework in a typical language. But in this case, I mean, the way that we're using it as application authors, like, yeah, it basically kind of feels like a framework. There's like, we give it a model, we give it this init, update, and render thing, and then it just makes a window happen. Okay, so with that in mind, let's take a look at the longer sort of breakout example. Okay, so we have the, at the beginning, let's say, here's our app. I'm saying I want to create an executable named Breakout. Package is exactly the same. Here we do actually have some imports. So I've got bounds, elem, and event. These are all types that I'm importing from there. And then the provides is exactly the same. So I defined a bunch of constants up here, like width of the paddle, height of the paddle, yada, yada, pixels, ball speed, all that good stuff. My model's a little bit more complicated than it was in Hello, where we just had that one text. So basically, this is my whole application state. I've got the height and width of the screen. And this is so if I want to resize the window, it can repaint, with the new dimensions. We have the X coordinate of the paddle. The paddle only goes in one direction, left and right. The ball has X and Y because it can move up and down. And then also the delta X and delta Y, which is like each tick, how much does it move? How many pixels does it move? I put some type annotations on here. So Rock is a type checked language, but as you saw, like I don't need to do that. Like here we have no type annotations and everything worked. But for this longer example, I would typically choose to put type annotations on these things. But since Rock has like 100% type inference, you don't need to. So here I'm taking the init always takes the bounds as of the screen, like the initial screen width and height as its input, so that the platform provides it to that, so that you can do your initial render and have those set properly. And then its job is to return a model. So here we're storing the screen height and width in this model record. We're calculating the paddle X based on the half the screen width, and then also calculating or subtracting the half the paddle width. So it's sort of like right centered in the screen, calculating the initial ball coordinates and the initial delta based on the ball speed and the width of the screen. Update's a little bit more interesting. So this is basically, we get every time an event comes in, such as a resize event or a keyboard event, it calls this function passing the current model, so the current sort of state of the world, and then the event that happened. We could make this fancier and sort of situationally subscribe to certain events. This is something that you have in Elm. Elm architecture calls this subscriptions, but for this basic demo, we're just like, let's handle all the events. Okay, not all the events. We have this underscore for if an event comes in that we don't care about, but we're really only paying attention to these four. So one is window resize. So if the window gets resized, a new size comes in through this event. We basically say, take the model and then return the same model, but with these fields changed. So we have width is size.width and height is size.height. So this is pattern matching. Rock is in the grand tradition of languages like Elm and Haskell, it's got first class pattern matching built in. Here I'm using a little bit of a more advanced pattern match where I have key down, and I'm actually hard coding if the key was left, then do this. If the key was right, do this in a separate pattern. Another way you could write this is you could do key, and then you could say separately when key is left, left do this, and then right do this. So that would work too, but the way that I chose to do it for this demo is just doing them both in line like this. So it's basically the same thing as the resize, except I'm setting paddle X and paddle Y to be a little bit different based on the paddle speed. So sort of moving the paddle left and right that many pixels, depending on which key you pressed. And finally, we have tick, and tick is basically just like an animation tick, like a new frame comes in. So this just periodically comes in on a timer. And this tick function is basically, give me a model, I return back a new model based on all the stuff that happened in that animation tick. So I used a pipeline syntax here. So I start with model and then pipe it to move ball. If I had collision detection and stuff, I might do update blocks or something like that to see if the ball collided with one of the blocks and need to remove the block, stuff like that. Maybe I'd say update score or something like that. Basically I could just keep pipelining as many of these operations as I want to do on the model. But for right now, we just have move ball. So here's what move ball does. So it calculates some new coordinates for the ball. It looks at where the paddle currently is and tries to figure out if the ball is crossing over the paddle. It's, it started the frame up here and then it ends the frame either in the middle of the paddle or maybe past it, depending on how fast it's moving. And so we detect that and say okay, if it collided with the paddle, then we want to bounce off of it. So we calculate this sort of multiplier that we multiply the balls dx and dy, the delta x, how fast it's moving, and that basically will either if it didn't hit the paddle, keep going in that same direction. If it did hit the paddle, then reverse direction and start going in the opposite direction. There are definitely fancier calculations you can do here to make it work differently depending on how fast the paddle's moving and stuff. But again, for this demo, just decided to keep it really simple. But you can already sort of see the structure of one of these things. We have this update function that's model, our current application state, event comes in, give me a new model. That's it. Everything else is just helper functions being called from update that ultimately will just result in a new model happening. And then finally, we have render, which gets called every single time the model changes. So every time this update gives back a new model, the platform will just run this render. So here we've got, we're sort of calculating all the things we need to calculate about the blocks. Basically, each of the blocks gets a color based on its like row and column. So, could have also just like hard coded that, but I decided to just make it sort of algorithmic. So that's where you get that kind of gradient looking effect. Calculate the width of each block based on the current width of the screen. So that way, as you resize the screen, the blocks like get bigger and smaller so that they're, appropriately sized within the screen, no matter how big or small you make it. And then finally, I translate all these blocks that I've just built up into rectangles. So this is sort of like this rect primitive is like the primitive that the actual the game system itself expects. So let me zoom out a little bit just so we can sort of see more of this on the screen at once. Basically, for each of these blocks, what I'm doing here is I'm making two rectangles, outer and inner. And that's where I got the sort of border effect. Is I basically, again, just doing the simplest thing possible, draw one rectangle and then draw another smaller rectangle inside of it with a slightly different color. So this kind of gives you a sense of like how primitive some of these platforms are right now. Obviously, we could introduce a platform primitive for like border, but we just haven't done it yet. So since this is the only primitive I had to work with for this demo, that's just how I did it. Simple enough. Also, you might have noticed that the ball was a square and not a sphere or a circle. That's because, again, only have rectangles to work with so far. Obviously, like anybody can add to these and like add to this platform and give it the capability to draw circles and stuff. But, for this demo, didn't have that yet. So just went with a rectangle. And then finally the paddle. And then basically we concatenate all these together. So all the rectangles for the blocks and the paddle and the ball. And that's our render. And then we, just like with hello, we finally end with this little, by the way, platform, here's my program with all those different pieces. Okay, so putting all that together, that's how we got the Breakout demo. That's the whole game. So obviously, if you wanted to make this game a lot more interesting, you could add a whole bunch of logic to this and like, make it more fun and have it use text like we did in the hello example to draw the score and stuff like that. Also, if you wanted to make the platform more powerful, you could get into platform authorship. Like anyone can make any of these platforms. This is, it's like completely up to you if you want to just stay in the application world where you're only dealing with .rock code, or you can get into platform development where you can get sort of under the hood and sort of start tinkering with some of that other stuff. Okay, so that's the demo. Let's talk about like how we're doing as far as like some of these goals. So as far as programmer experience, one of the things that I like about where we are right now is that it really doesn't take a lot of knowledge to like get Hello World up and running. This is pretty short in terms of lines of code, but more importantly to me, it's pretty low on concepts. I don't need to teach you a whole lot of different concepts to understand how to make a basic game application using this platform. I'm happy about that. Also, I didn't demo this, but one of the things that Rock is definitely taking inspiration from Elm on is error messages. So Elm is like famously really, really good at giving really helpful error messages. And we have very much tried to keep that spirit. And also in a lot of cases, as you will see in a second, like taking the errors basically directly from Elm and just like modifying their presentation a little bit. So here we have an example error, type mismatch. The model record does not have a wit field. This is Philly ETE, so I thought I'd put wit in there. If you're from Philadelphia, you know what I'm talking about. So basically, it's got the little squiggly red underline there, and this is the problematic part, right? Wit size.width. So it says model record does not have a wit field. There may be a typo. Here are the model fields that are most similar. So it sort of sorts them by similarity, and width is right up there on top. It's like, oh, okay. And then it even like bottom lines it for you. So maybe wit should be width. So yes, that is in fact the exact problem that happened here. But I've definitely worked in languages where this error would be like one line long, and it would just say something like, could not find wit on model, the end. So I really appreciate like having all of this context of like, here's exactly where the error was. Here's not just the underline, but also like, here are multiple suggestions, and also just bottom lining it for me. Here's the most likely suggestion of like what the problem was. This error message like comes from Elm. We just kind of like modified a little bit for Rock. And we're really trying to like, again, like aim for that really high bar that Elm has set in terms of like programmer experience around error messages. In terms of resource usage, so I took some measurements earlier when Zoom was not running on how things were running. Everything ran smoothly, and in terms of like memory usage, that's something that you can actually like directly measure. So Rocktris was running about 2 megabytes. Fireworks demo was about 33 megabytes. Remember, Rocktris was running in the console though. The Fireworks had a whole window application. Breakout was like 68 megabytes, and then the Hello application was about 25 megabytes of like. So that's basically like the just the window with the text on it was 25 megabytes. You might notice there's a pretty big difference between Hello and Breakout, and you might be wondering like how much of that is like all the additional graphics stuff that Breakout is doing versus how much of that is the Rock application code. And we actually have a really pretty easy way to memorize to get like a proxy for what that is, which is by looking at the size on disk. So Rocktris size on disk 2.4 megabytes. Fireworks was actually 0.1 megabytes. It was like 100 kilobytes. Breakout was 7.1. Hello was also 7.1. Hello and Breakout, even though we saw the difference in code size in terms of like Hello World was like 14 lines of code, Breakout was like literally an order of magnitude more, was like 140 something. And yet the delta in terms of the compiled application size was 49 bytes. So all of that extra Rock code compiled down to 49 bytes worth of extra machine instructions on disk, like comparing these two applications. That's it. So why is there such a huge gap in terms of the memory usage? And that really comes down to the graphics. Like Breakout had way more graphic stuff going on screen. The gap shouldn't actually be that big. Part of the reason for that is that I know that there's some duplication going on in the platform, which reminds me, one of the things you can see here pretty clearly is that like platform optimization can make a really big difference in terms of like memory usage as well as disk usage. So Rock, the language, is trying to make things as, in terms of like the code that it generates, as resource efficient as it possibly can be. But the platform that you're building on top of really makes a huge difference. Like Rocktris, because it's only using the terminal, doesn't have nearly as much memory as these platforms that are doing an actual like spawning a separate window and drawing graphics in it. And you can see that like Fireworks, because it's built on a different platform than Breakout or Hello World, is actually just this tiny amount on disk in terms of the application size versus all these others that have a lot more going on. So you might also be wondering, well, hang on a sec, Fireworks was actually spawning a window and drawing graphics to it, and Rocktris was in the terminal. How come Fireworks was so much smaller than Rocktris? Like, how could that be? And again, it really comes down to the platform. So each of these platforms are implemented with different underlying non-Rock technologies. So Rocktris was just using the terminal, but importantly, it was using a Rust-based terminal, like TUI type system for all the like keyboard inputs and like the animations and stuff like that. And that underlying framework had some overhead to it. Fireworks was using the C++ library called SDL2, which obviously has a lot less overhead than that. So that's how the compiled application could be so much smaller. It really had a lot more to do with the platform that each of these were built on than the actual Rock compiled machine code itself. And Breakout and Hello were both using WGPU-RS, which is a Rust library that was even bigger than Rocktris. So again, this really is an example of like Rock, the language, trying to compile to the smallest possible code, but the platform making a really big difference in terms of total resource usage. In terms of running very fast, I give a whole talk on how Rock is able to run fast. It's called Outperforming Imperative with Pure Functional Languages. Here's a link to it. This is at Strange Loop last year. One of the things that sort of has a bright line distinction is things that compile to machine code and like how fast they compile to, or how fast the machine code is that they compile to, versus languages that are interpreted with or without like a JIT or like a VM or something like that. So like C++, you have LLVM, which is a really good optimizer that spits out really optimized machine code, and it goes straight to a binary. Rust is the same thing, but Rust has a little bit more overhead, typically speaking, because Rust does what's called bounds checking, whereas C++ typically doesn't. Technically in Rust, if you want, you can skip bounds checks, but like that's not how the standard library is set up, and it's really discouraged in Rust. There is a runtime cost associated with bounds checks, but it's really important for memory safety. So culturally, this is done in Rust way more often than C++. Does make the binaries run a tiny bit slower, but I think it's totally worth it, which is why Rock also does that. But the big difference between Rock and Rust and C++ is that we also do reference counting for automatic memory management, whereas Rust and C++ do not. That's a big deal for ergonomics because it means you don't have to really think as much about memory. It's just like, I don't know, it gets deallocated, fine, I don't really think about it. Because we do reference counting instead of tracing garbage collection, you don't get garbage collection pauses, which is quite nice. But obviously this is like a totally different category of ergonomics, but also of overhead. Like reference counting definitely does add overhead, but importantly, it doesn't add much. I mean, if you look at like all of those, like the model that we had there, if you took that exact same model in Rock and ported it to C++ or Rust, it would compile to exactly the same thing. There is no overhead in that model compared to C++ or Rust. Where the overhead comes in is actually in Hello World, where we had a string. You would get a little bit of overhead there if that string were longer. But actually, because Rock does a small string optimization, in that case, the Hello World actually would have been exactly the same as even C++ in terms of how the string is represented. But now you compare that to something like Python or JavaScript, or even something like Java or C#, where they're interpreting either some bytecode or some source code directly. And yes, they can have a JIT, but usually JITs only kick in around loops that are like 4,000 iterations plus, which literally would not have come up in any of these demos. Like none of these demos would have actually had a JIT kick in because none of the loops would have been big enough. Granted, JITs can do some things outside of like hot loops, but I know that in a lot of cases, it's pretty easy to think of two things and not maybe think about how contradictory they are. One is that obviously C++ and Rust run a lot faster than Python or JavaScript or Java, which is why there's this big meme of like rewrite it in Rust to make it run faster. And yet at the same time, people will also think, oh, well, JITs make interpreted code fast. Well, they can't both be true. There's some difference that's making Rust faster. It's not magic, it's lack of a JIT. And so that's how Rock is able to sort of like try and be closer to like Rust and C++ in terms of performance than JITted languages of like VMs and things like that. If you want to learn more about the details of how Rock does this, including like all the representations that we use for all these data structures and stuff and how all the low-level stuff works, gave a talk at Handmade Seattle about that. So if you're interested in like getting really deep under the hood, check it out. And finally, we have cross-compiling. So here we've got a Mac laptop, a Windows laptop, and a Linux laptop. By default, if they are compiling binaries, like actual like machine code executables, like we saw there where I was like compiling fireworks, the executable, you've got your system toolchain that only really knows how to compile normally binaries for that system. The only language I know of that's sort of like general purpose and cross compiles to other toolchains is Zig. And the way that Zig does it is quite literally by making sure that Zig actually has not only, if I'm running it on a Mac, the Mac system toolchain, but it actually includes in the Zig language, the Linux system toolchain and the Windows system toolchain so that it can do all that cross-compiling. But as we'll see in a second, Rock doesn't actually have to go that far because we've got a bit of a cheat code that most languages can't do. So if I'm on my Mac and I want to compile to Mac and Linux and Windows, the way that we do that on Rock is with precompiled platform binaries. So basically, whoever was making that platform, like the one for like Breakout that had like the model view and update, or like Rocktris, whatever platform that's running on, the platform author uses their systems toolchain to build a precompiled binary for just the platform part of Mac OS, Linux, Windows, whatever different combination of targets they want to have. They've done that. I, as the application author, don't care. I don't think about that. I don't have to worry about any of that stuff. As you saw, I was just writing Rock code the entire time I was, working with all these applications. That's the platform author's business. But if the platform author has done that, now I, as the application author, get to have cross-compilation. And basically the way that this works is that I get from my platform a different precompiled binary for all the different targets that platform supports. So Linux, Mac OS, Windows, also like x86 versus ARM, that distinction matters here, 62-bit versus 32-bit, all the different combinations that they support. I just have those as precompiled binaries. They tend to be pretty small, only a couple of megabytes. I don't have to have the entire system toolchain for that target, just the precompiled platform binary. Once I've got that, I basically am like, okay, cool. I want to cross-compile to another target, like I demoed of cross-compiling to Linux. Well, Rock, the compiler, knows how to compile application binaries for all those different targets. Like it knows how to spit out Rock application code for Linux or Mac OS or Windows, or well, not Windows yet, but we're working on that. But then basically it just links those two together to produce a binary executable of both. So all of the system linking stuff, all that system-specific toolchain stuff happens on the platform side ahead of time. I, as the application author, don't have to worry about it. And the way that we're able to link these together is by using this technique we're calling surgical linking. Brendan Hansknecht, shout out to him for making the surgical linker work. Right now, it only supports 64-bit Linux, which is why that was the one that I demoed. We're working on it for Mac OS, and then in the future, we'll also get to Windows. But the important part is that like the system is set up such that we can do this, and now it's sort of just a matter of time before we get those other targets supported as well. basically the goal that we have is that ultimately, once we have like a package manager, when you install your platform package, like you say, I want to install this platform for doing game development, or hopefully in the future also application development. So I could actually make a Winamp type thing, like a media player in Rock, using these same kinds of primitives and techniques that we talked about. I just automatically get all the precompiled binaries. They just ship with it. I don't have to do any extra work. I'm just like, cool, I installed it, and then the compiling to Linux feature just works. So that's the goal, but we're not there yet. We don't have a package manager yet, but that's sort of like something to look forward to in the future. Definitely, there's still plenty of things still to do. Making non-game UI platforms. Again, anyone can do this. Like if you want to go to rockdang.org and like download the compiler and like just start making your own platform, you can do that right now. If you want to cross-compile to more targets, that does require changes to the compiler. Mac OS is a work in progress. We haven't started on Windows yet for cross-compilation, but definitely planned. We have some ideas on how to shrink those compiled binary sizes. Like I said, a lot of what comes out of those compiled binary sizes has to do with the platform, but we can do more to strip out like unnecessary platform code, even though we've got the precompiled binaries. We know ways to do that, but we haven't done it yet. Package ecosystem definitely requires having a package manager, which we don't yet. And then finally, just a whole bunch of like compiler bug fixes, improvements to the language and stuff. Like I said, not ready for production use yet, but we're working on it. And now we actually have more than one person working on it full time. I'm actually getting paid at no rating to work on Rock full time because we want to use it in the future. And I'm very excited. It's super awesome. And I'm not the only one. So expect more good things to come. Okay, before I wrap up, I just want to say thank you. Shout out to Jared for making Rocktris, and also for making file names happen on error messages. That's been a long time coming. Brendan for making fireworks, and also the surgical linker. Like, huge shout out to him. That's an amazing piece of technology. Brian Carroll for working on all the WebAssembly integration. This is not a talk about WebAssembly, but like all of that, all the stuff that we're talking about in terms of like compiling to binaries totally works on WebAssembly, and Brian's been a huge part of that. Also, shout out to Anton, Folkert, and Ayaz for helping with the Breakout demo. There were a lot of like compiler bug fixes and stuff that I discovered while making the demo, and shout out to them for fixing those, and to Anton for making the underlying platform work. Finally, I just wanted to note, I love this message. This was from somebody commented on a pull request that they made to the Rock repo. I think it's a great sign about your compiler design that a high school with no prior experience with compilers or Zig or Rust can make a pretty fundamental change to the language's behavior in the space of 3 days. Feel free to use me as an example in your upcoming talk to persuade other developers who might be on the fence about contributing to Rock. Done. So if you're at all interested in contributing to the language or any part of the ecosystem, please feel free to get in touch, because there's plenty of stuff to do. Okay, so summarize all the things we just talked about. Started off talking about Winamp and sort of like these like 1998 desktop application experience. I have all these fond memories of how it had this like distinctive style, which granted is kind of the norm now, light resource usage, and it ran really fast. Modern desktop apps, I mean, yes, they kept the sort of distinctive, nice style, the non-native look and feel, but in a lot of cases, they have like massive resource usage, like way more than what seems reasonable for what the app is doing, and like delays, like loading spinners, and just general lagginess all the time. We want to try and do better than that. We want to try and give you the like delightful programmer experience that I've experienced with Elm, but while still having light resource usage, only a couple of megabytes, running really fast, like competitive with like C, C++, and Rust, give or take the reference counting and bounds checking, and even with cross compiling. So you don't have to spin up like a VM just to build on Linux. You don't have to spin up a VM to build on Windows. You can just from your Mac build for all the different targets. And we don't have all the different targets yet for sure, but we're headed in that direction. We already got it working on Linux, so the system works at the very least. We talked about programmer experience in terms of like hello world being pretty small and simple, and like not a whole lot to learn. Talked about resource usage, specifics, and how it's pretty light, running really fast, and of course cross compiling. So that is the current experience of native desktop apps in Rock, and where we're headed in the future. Thanks very much.
It's not often you get to see a language being made these days. I mean, I know that a lot of people are working on them, but this one has potential, especially teamed up with Zig.
Yes.
All right. So do we have any questions for Richard about why wasn't Elm enough?
Why wasn't Elm enough? So Elm compiles to JavaScript and is very much designed for like building UIs in the browser. And so I basically was like, there's a lot of other use cases that I want to do, want to use an Elm-like language for. And so I figured, why not build it?
Makes sense to me. I mean, who has the time? All right, let's see. Somebody's typing. Somebody's typing. I see typing. All right. Thanks very much for the demos, Richard. Very cool to see you things moving forward. No questions. There's no questions. No questions. Okay, well, you know what? It's okay. You all should come tomorrow to our panel. We are going to do a small panel on typed versus untyped languages. People are always wondering why these types are great and why types are not great. And, we asked Richard to speak tomorrow because, people always think of TypeScript, which is like a JavaScript with types bolted on, but there's like really some great, really typed languages out there like Elm and Haskell that really show the power of types. So we wanted to be serious about this discussion.
Absolutely.
So we'll see what happens tomorrow. Okay, Gary, does Rock going to have a standard library of APIs, dates, collections, etc.? You can write it.
So Rock does have a standard library. It's intentionally pretty minimal though. So it definitely has, it's all data structures. Dates, the plan for that is to have those handled separately, like in a separate package, not in the standard library. There's a whole like philosophy around that. But yes, definitely we'll have a standard library. I think people would probably not describe it as like batteries included, but rather more of a like small and simple, relatively speaking, like it's probably going to be under 10 modules total. And then like a really nice package ecosystem where like you can get access to like, a sort of de facto standard where it's like not officially the standard, but like you can use a different implementation if you want, but there's probably going to be like one popular one that everybody uses in practice is my prediction. We'll see.
All right, we got some questions now. How will the model be rendered into things like sound? Thinking Rockham.
So for this demo, I just had the simplified version of update that just returns a new model. But like, so this is something the Elm architecture has, is basically like you have update return two things. One is the new model that you want, like the new application state, and then also a list of sort of like tasks that you want to run, like play a sound, like write to the file system, maybe read from the file system, like you have like a save load functionality in your game, anything that's sort of like an effect. It's sort of like traditional in Elm to have like this progression where you start off with like this simpler version and then you sort of like upgrade to that when you need it. So for this version, I didn't demo that, but if you watch my talk called, what was it? A Taste of Rock, that's on rocklang.org. I demo like running effects, like reading to file system and writing from file system. So you can get a sense of that.
Is there any kind of interop, like with C libraries and stuff like that are compiled? Like, .so, like ImageMagick or, like that kind of stuff?
Yeah, so the interop is basically all done through the platform. This gets into like security questions. So if you check out my talk, The Edges of Cutting Edge Languages, which is also on rocklang.org, you can learn more about that. So definitely like the platform does all sorts of interop with C. It's sort of up to the platform whether they want to allow application authors in their particular platform to do that or not, which is important for security reasons, which that talk goes into more. But short answer is like, definitely there is some done in the platform. Maybe it's supported in the application, but it depends on the platform.
That makes sense. Everybody wants the easy way of, who wants to write their own sound library? When you have like all of this stuff available.
This is a good example where like the platform for like Breakout, for example, is handling all of the like, rendering stuff, like all the shaders and whatnot, to render the graphics card. So like, yeah, that stuff is not all written in Rock, that's written in Rust. But as the application author, I don't see any of that. I just deal with Rock code. That's it.
Cool. All right. Oh, I see more typing. Maybe it's a question. Maybe it's like, hey, this was great. That's the one. I miss Slido. We should have used Slido. Well, we got Martin typing. That's going to be a question for sure. Okay. Good luck, Richard. Learning a new languages are challenging. You're creating a new one. Yes, for sure. I definitely don't have what it takes. Rock seems to have developed down a path very far from what you first had in mind. Can you talk about what journey this has been like for you?
Oh, I don't think it's that different actually. Like in terms of what I had originally in mind. I mean, definitely some things have changed, but so far they've been pretty small API changes. I mean, I guess like uh they haven't changed that much since the first time I talked about it publicly. Obviously, there was like a whole design phase in like 2018 when I was like figuring out exactly what I wanted it to be. Um, I'm sure things will continue to change at some point, but I guess because we have such a strong starting point of Elm, there were like a lot of the questions where I was like, I want to do it either like I want to do it exactly the same as Elm, or we're doing it differently, but not so differently that I'm worried that it's going to feel really different. Um, yeah, I mean, so far it seems like it hasn't changed that much at all. At least I'll say this: it's changed less than I expected it to. I would have assumed based on how most of my projects go that like by now it would look totally different, but it actually doesn't, and I'm pretty happy about that. Pleasantly surprised.
Yeah, it's nice to realize your dream. So what aspects does Zig actually play inside your language? You just use it for like writing the compiler and stuff like that?
So that's a great question. So the Rock compiler is written in Rust, but the underlying, so the low-level stuff that goes into making the standard library is written in Zig. So maybe you could say that the implementation of the like Rock primitives in the standard library are written in Zig. Part of the reason for that has to do with the two languages like relative strengths and weaknesses. Like Zig is like really good for dealing with like really low level, like unsafe mappings between like C type things, which is kind of what we need to do for those primitives. There's a lot of just like innately unsafe stuff. We initially tried to write the standard library in Rust, and it was just like nonstop using the unsafe keyword unavoidably. And Rust doesn't really give you a whole lot of help when you're in that sort of mode of like you doing unsafe stuff. It's sort of like just try not to do it, and if you have to do it, you're on your own. Whereas Zig really embraces that and is like, oh, if we if we assume that we're going to be dealing with a lot of unsafe stuff, we'll give you a lot of help with like testing and all this stuff to try and make that easier and less error prone to work with. So we found Zig to be really nice for that use case.
Right. Any more questions? Let's see. Room A. Out of curiosity, what made you choose the name Rock? Like Dove, Rock Dove.
So I have a little like blurb about like where the name comes from, but I don't remember what made me choose it. I just remember thinking of it at some point and really liking it and going with it. So Rock is the name of a mythical bird, which I actually learned about from a Magic card back in the day. I used to play a lot of Magic the Gathering. So that's like what it's named after, which is why the logo is like an origami bird. And it's origami because it's as an homage to Elm's logo, which is a tangram. It's something where you can make surprisingly many things out of a small set of primitives, like a tangram puzzle. And the same thing is kind of true of origami. Like you can make a surprising amount of things using just folds, which are also a functional programming concept. And so like, Rock is not the same as Elm, but it's very similar. And origami, I think, shares that in common with tangrams. Very, very similar, although they're obviously not the same.
All right, and then there's Microsoft is coming up with MAUI, multi-platform app UI. At high level, how is Rock going to be different from MUI? I don't know.
I actually don't know anything about that Microsoft project, but I mean, I guess at a high level, I guess if you are familiar with that project, I mean, I just demoed the whole experience in Rock, right? It's like you write it and then you compile it to a different target, and that's what you get. I'm sure there may end up being, differences when people like flesh out these platforms more, and like maybe they want to give you a way to do something like Mac specific or Linux specific or Windows specific, and the APIs for that might be different. But really, all the fundamentals are what I just demoed. That's the whole experience. So I guess if you're familiar with the experience Microsoft is going for, you can sort of diff the two and decide for yourself what the differences are.
All right, we have a very interesting question here. Would Rock be a sensible choice for writing microservices?
Would Rock be a sensible choice for writing microservices? I mean, it's definitely going to be hopefully a very good choice for writing servers in general. Whether you want to use microservices with it or not, is up to you. But that's the main reason that NoRed Inc. is paying me to work on it now, is that we do want to use it for servers. So that's going to be the main use case that I'm going to be focusing on over the course of the next year or so. And that and like command line apps, the other thing we want to use it for. Stay tuned for more on that. But yes, I certainly hope it will be useful.
So you're hoping to replace your Haskell backend with Rock eventually?
I mean, if it's good enough, certainly. We don't really tend to like rewrite stuff unless we have like a compelling, motivating use case too. But like, I mean, I think if I do a good enough job with it, then we will hopefully choose to use Rock over Haskell and Ruby, which is what most of our backend is written in today. Just because we found it to be better in various dimensions, like compile times, runtime performance, and like ergonomics of error messages and stuff like that.
Okay, well, we went a little over. 3:45. Okay, so no, we're actually 5 minutes under. Okay, well, thank you all very much for coming. It was definitely an enjoyable talk for me. I love to see how Rock has progressed over the last year. It was great to have it introduced last year for us.
All right, take care.
Thank you, Richard.